we are now at the point where we want to take the data that we've created. So for each fencing clip, so we had all these fencing clips, we have this CSV file, computer separated variables, values? I don't know, probably values. I assume it's values. And we're going to take these values and we're going to try and make some sense out of them. Yes. And so the idea here is these are the accelerations of the fencer. This is the left fencer, this is the right fencer, and they're all normalized to 1. And what's going to happen then is and then this is where the lights turn on. This is the red light, which is the same as the left light. This is the green light, same as the right light. And here's when the right light turns on, here's when the left light turns on, both similar times. And then, so this will be the data we input. And then we're going to take that and we're going to combine that with the data we have from another CSV file. This is one where it has to do with eclipse. And this, we're going to have the middle frame right here. So this middle frame right here is going to correspond to the video file we're just looking at. And this tells us if it's a left, if the score is right or left. All right, so that seems reasonable. First thing we're going to do then is try and figure out, actually I should probably combine these. That might make it sense. So I'll do that quick. We'll see where that goes. Yes, this is what I wanted. So now we have the data we're going to analyze, which is this, and the answer we want, i.e. the target, is right there. So excellent. Though that feels weird that the red light turned on so early. That one might be a fluke. I might want to take a look at that. This one looks more realistic. Yes. All right. Excellent. Now we have our acceleration files. So we have this data going in, and the data we want coming out is that. All right. So I would like to create a model that inputs. Let's see if I can. Ooh, maybe I can. Yep, I'll just copy this. Inputs a CSV file of, I'll say similar to, and the result, I'll say target. I think target is the more official term. This we have left. And the target is left. Let's just see what it says. We'll go with this. So I'm thinking about a LSTM model, long short term, but I think that might be kind of dated now. Blah blah blah. Ooh. Random forest classifier. I have no idea what that is. Victory, blah blah blah. This code uses creates a random forest classifier model, trains the model, makes predictions of the testing data and collect. No, this is a basic example. Maybe. What is a random forest classifier? What is a random forest classifier? No idea. Nope. Decision trees. So the data that I am using is time specific. So I was thinking of something along the lines of an LSTM, long short-term memory. Basically says that it goes sequentially in series from beginning to end, and the time in there matters. Blah, blah, blah. A temporal dependencies. Oh, that's a good word. Temporal dependency. Phrase, I guess. Are particularly effective hit and long-term dependency in context data or no, blah, 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 learn. Incorporating dimension, blah, blah. You can use deep learning models such as TensorFlow to implement LSTM model. I'll do maybe what are LSTM models a bit dated? What could be some alternatives? What could be some alternatives? Maybe. TensorFlow and PyTorch. Yep, I could use both of those in Google Colab. Well, the user great success, blah blah blah. We're doing at the field deep learning concept evolving. So we have gated recurrent units. Ooh, that's kind of nice. Transformers. Tension mechanism to capture relationship between different elements in the sequence. That kind of sounds like what we want to do, because we want to have an acceleration at the end, I think. So maybe that acceleration, I don't know. Maybe we'll try a transformer. Long range dependency have shown superior performance such as machine translation. More about natural language processing. Okay. Temporal convolution. One-dimensional. I don't know if this is a they came mode. Dealing with tasks where local patterns and short-term dependencies are more important. Maybe. I've heard good things about transformers. I have no idea. Or we could do a gated recurrent unit. I have no idea. What would be the pros and cons of using a GRU, gated recurrent unit, as opposed to a transformer? Maybe. So it says effective for shorter sequences. Difficulty capturing long-term dependencies. Limited parallelization. Sensitive to sequence length. So for capturing long-term dependencies, parallelization, scalability, complexity, higher computational data requirements. So I'm not sure what they mean by a longer. So they say GRUs are good for shorter. So a gated recurrent unit. Oh, just one C, recurrent unit, is less effective with longer sequences. What would be considered a long sequence? So most of our sequences have like 60, 70 values. When they say long, I'm wondering if they're thinking like thousands. So ours might be considered short. Yep, I think they're, let's try a GRU model. All right. How could, actually it would be easier to, which would be easier to implement? Would it be simpler to implement a gated recurrent unit or a transformer using Google Colab? Okay, so it looks like I can do either one. All right, so I'm going to say write some code. Okay. Can you write a code snippet that would mount my Google Drive? Load the CSV files. Would mount my Google Drive and create a gated recurrent unit model to train based on the CSV files found in the directory. And the directory here is, I think it's acceleration underscore files. Acceleration underscore files. Acceleration underscore files for each file, for each CSV file in the directory. Let's see, I'm going to say the first 1, 2, 3, 4 for each file in the directory. The first 4 columns are the inputs, and the 5th column, which is the same for each row, in the CSV file, will be the target. So what I'm saying is input, output, and really each row, each of the, I guess, 50 rows of data we have here, so it's 50 times 4, so it's 200 points of data broken up into groups of 4. So I guess 50 sets of data or 4 sets. All right, so it gives me some code. All right, 97% accuracy seems reasonable. Yeah, let's go for that. All right. So now, hop. So I'll go back to ChatGPT. Excellent. Whoop. I have used this code to train a model. How can I save this model now to my Google Drive for future use? Boom. Yes. And hopefully it'll give me some code. Up all the way down. That looks like it wants me to train the model again. Since I have already trained the model, does this code train it again? So I just want to save the model. Boom, saves it. This code defining we load the pre-trained weights, blah blah, then save the model using model.save. This is our location. So it's going to be model.save, model.h5. So let's see if that works. So let's do, we're going to come down here, we're going to save the model. Hup. Okay, we're going to check over here. Actually, I'm going to add that bit up here. Whoop. Perfect. Maybe. We'll see. Get rid of that. And we'll see over here if it loads the model. And it's just model.h5, or h5 is a extension for the model. Okay, so it looks like it just did that. Okay, so maybe true. So now what we want to do is we have some clips. Just pseudo-random fencing clips that I grabbed from another strip. Like so. The issue, one of the issues going to be, is that it looks like the overlay lights are turning on slightly before the lights of the actual score box. So the lights are turning on before they actually hit, which I think is happening because of something like, there's probably the camera has some sort of compression or analysis it has to do before it basically sends the video data over to the computer, and so the computer is able to get the data from the score box sooner than it's able to get the camera because there's a delay, and that could be dealt with, but it wasn't. So that's why we get the light turning on earlier, I think. So I'm going to take these clips, clip 1, 2, 3, and analyze those, try and use this. So first thing I do, go back to our detection and tracking. So main code for detection and tracking. So what we do is it looks like this. So, all right, so now what we want to do is, can you modify the code? Nope. Detection and training, this code right here. So that it will instead run the function run inference on the video files clip1.mp4. I think it's .mp4. .mp4. .mp4 clip2.mp4 and clip3.mp4 in the main directory instead of, and the files in output videos instead of the videos, the files in output videos. Yeah, so I'm basically just saying run these other run it on these others instead. So let's see how that works. Certainly, blah, blah, modified code. And I might just look to see how it's modified. We'll see if that works. Da da da, ba da bum 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 bum. All right, and I'm just going to do add code here. We'll put some text above it. And we'll say runs just the videos in a list. And I'll call this runs all videos and output videos. And this, yep, 2 lights. Excellent. Okay. We got this. So now come back to our model that we trained and we'll try to run it. Cross your fingers. Maybe. We'll see if this works. Come on. Do it. I don't know what that means. Oh. I think this is what I wanted. So this is the classification, I think, but it's from a 0, it's a percentage. So I received the values of this when I ran the code. Could you explain what they mean? Ba-dum-bum, ba-da-bum-bum-bum-bum. Come on. Excellent. So, excellent. Can you modify the code so that it will output left? So let's see. We had a high probability. So low percentage, probability class right. Okay, left, I'll put left or right touch. So let's see here. In this case, high percentage class is touch right. I'll put right if value certainty, the probability is greater than 50%, and also print the probability if the probability is less than 50%. Then print left touch, and we'll do the percentage as 1 minus the probability. There we go. So this will basically just be like left or right. Ba-dum-bum. And then it basically inverts. So it's, if it's like 99%, it's like, oh, that's very much right. If it's 1%, then it's like, oh, it's 99% left. Yeah, let's see if this works. We're just gonna grab this and go for it. Confidence. Ew, what are you doing? You're going through each. No. Hup, hup. Running all the files, run just clip 1, 2, 3 as in this code. There we go, and it's just trying to run all of the video files, which I don't want to do them all. So it's like, oh, do some of these, blah blah. Clip 1, 2, 3. Yes. Maybe. Boom. So we have right touch, left touch, left touch. And yeah, okay, I'm good at this. So it seems to be very certain, like 98%, whatever. So right, left, left. So if we come back to our videos, let's look at clip 1. So clip 1, it said was right touch, which makes sense, specifically because there's one light, so strong confidence on that one. So the second one, it said was left touch. Let's see what goes on here. Maybe. I'm not 98% confident like the model is, but I'm like, maybe. And then clip 3. So I'm going to say the last one actually probably was left touch because that was score 1.5. This is now score 2.5. So it's probably correct. So now for this one, go back to the model. It said left touch, high confidence. I think this one was given touch right, but this is such an unusual touch that I'm not going to hold it against the model. It's like, yeah, that's a nuance that would be hard. It would need a lot more training clips similar. This is an unusual touch, so I imagine the clips we use to train it were probably not this. So it is at least understandable why the model would be like, yeah, that's left touch. So if this actually works or not, I don't know. Have to do a lot more testing. This is just kind of an example of, hey, here's a rough and tumble example of how you could train an AI model. To backtrack, big picture what we did here, I know because there's a lot of stuff we did. We went through the data collection, basically made all these clips, we took all this big clip, made up into smaller clips. We used a bunch of computer vision, nothing really particularly AI related, just like, hey, here's an image, look for a very similar image at a very specific spot using an overlay. And that gave us a bunch of fencing clips, which we used trickery to basically determine if they're epee or saber. And then we also found when the lights turned on. Did it very inefficiently, probably could do it way better, but it kind of worked. Then we did some detection and tracking, which used, again, computer vision, but this time it used AI models, computer vision models, which is AI. We used YOLO V8 by Ultralytics, which is not really associated particularly with YOLO V3 and V4, different group of people, but I think they're trying to cash in on the name, which is understandable. Though maybe questionable, that's okay, I don't care. So basically we did that to track the video, which works pretty well. We were able to train it up like in like an hour or so on the hand, feet, torso, and score box. We really only used the hand and torso though. And then we just did some basically clever limitations on where the bell guard could be. It can't be too far away from the torso. And then we did some basic tracking algorithms, just some very concept, be like, hey, if it was here, it's, if it's here previously, here twice previously, we're probably going to expect it to be at this point right here. So nothing complicated. And then to train the model, we ended up using a GRU, Gate Recurrent Unit. I think there's lots of models we could have used. Transformers, I've used LSTM before, long, short term. This seemed to train really quickly, and it trained to very high accuracy, but that could also be because it basically just trained to the test. I didn't have a lot of models. If I had more examples, more clips, then it would have probably had more trouble training, because it would have, if nothing else, detected inconsistencies between referees. So train the model, super quick, like a minute, couple minutes, if that. And we saved the model. And then after that, we had this, we grabbed a couple clips and ran it, and it took about less than a second, so about 800 milliseconds to analyze the clip, which is interesting. That's actually longer than I would have expected, but that's okay. And it just ran the clips and analyzed them, gave us an answer, and as far as I know, those answers could be reasonable. So hope you enjoyed me kind of just walking through how you could do an AI model. This is very much rough and tumble. Someone want to do a better job, it would not be difficult to do a better job than I did here, because this is not well polished. Just kind of an idea of like, okay, this is how easy it is. This is how it's accessible to anyone. Anyone can do this, and hopefully someone will. So hope you enjoyed it. See you next time.